This is Brett Sanders at UC Irvine, and I'm speaking today about regional forecasting of street-scale flood inundation with a variable fidelity model. The idea here is that flood inundation forecasting could help to reduce losses, save lives, and minimize disruptions from flooding. But there's some significant barriers to real-time street-scale flood inundation forecasting. That includes uncertainty in forecasting, especially rainfall, but also stream flow and storm surge information. Computational demands are also a big issue. Fine-scale models require a lot of calculations, and trying to get those calculations to fly fast enough to stay ahead of the flooding is a challenge. So the questions that we're trying to go after in this presentation are twofold. One is we're going to look at how sensitive is a flood forecast skill to the precipitation data that we use. And we'll use both stage 4 precipitation data for a hindcast analysis, and we'll also use quantitative precipitation forecast data to look at a forecast. The second question we'll look at is how sensitive is the forecast skill to the fidelity of the model. And we'll present a model today that has a variable fidelity option that allows us to look at this question. All these questions are going to be answered in the context of Hurricane Harvey. So we are getting sort of a case-specific analysis done here, which might not apply to every flood event. So I'll just acknowledge that here. Okay, so we're going to look at Hurricane Harvey. This was the most damaging flood in the history of the U.S., tied with Katrina. It made landfall in August of 2017, enormously disruptive. To set up our Primo model, we started with 1/9 second topographic data, which was available from the USGS. We did not do any additional hydroconditioning or stream bathymetry correction, and that needs to be done at some point if you wanted to sort of further improve the model. But for the time being, we're just going to use this data. And we're also going to test upscale factors of 10, 20, and 40 to study the impact of fidelity on these calculations. Another thing we're going to do is look at two different types of rainfall forecasting. Either the stage 4 precipitation data that is reanalyzed considering both radar gauges and so forth, and produced after the fact. And then we also have the quantitative precipitation forecasting data products available. So we'll compare both sort of a hindcast data product and a forecast data product to see how sensitive the flood model predictions are to those two factors. For storm surge, which gets specified down here at the boundary of the model, we'll use NOAA tide gauge data to force the model. And for stream flow, we've just grabbed medium daily discharge for flows that come into the model. So we're not going to study that in detail or that. And the reason why is because in this event, precipitation was the main driver of flooding. And this gives you a sense of the spatial distribution of flooding in the regional scale of the model. So here you're seeing the regional extent of the flood model, flood simulation. You're getting sort of different levels of resolution in these graphics. And here you can see sort of the detail that the model brings in terms of flooding along streets and so on. So this particular model was based on the 1 hour stage 4 data for precip, an upscale factor of 10, and this is the larger model domain, which was close to 9,000 square kilometers. Okay, so now we're getting into some performance measures. The first thing we'll look at is gauge accuracy and runtime versus the upscale factor. So we'll look at model fidelity first. How do results change with the upscale factor? And in this case, we're going to look at the stage 4 forcing, which is our best available precipitation data. What we've done here is there's over 26 gauges that we're looking at in this analysis. So what we did was we plotted like the best performing gauges, median performing gauges, and low performing gauges. Okay, so when we look at the best performing gauges, you can see in colors here, red, green, and blue, what you're seeing is the upscale factor of 10, 20, and 40. Okay, and so for these best performing gauges, we're seeing sort of mean absolute errors of around, say, 0.36, 0.49, 0.63 meters. That's the accuracy you're getting at the gauge. And the Nash-Sutcliffe efficiency here is close to 1, 94%, 88%, 80%. So we're doing really well at some of these gauges. You can see, again, at this gauge, Nash-Sutcliffe efficiencies of like 90%, which is excellent. And also with the smallest upscale factor of 10, we're getting errors on the order of half a meter, which is, or mean absolute errors of say, even 0.3 meters, which is doing really good. Okay, so So then in the median, you start seeing that these numbers getting bigger. So now our mean absolute errors are closer to a meter or even greater. And at the lowest rank gauges, you're getting mean absolute errors of several meters or more. Okay, so that's a little bit of the distribution of errors across the gauges. When we summarize that in the table over here, you can see with upscale factor of 10, 20, and 40, and considering all 26 gauges, you're seeing how these average mean absolute errors are increasing, how the root mean squared errors are increasing, how the Nash-Sutcliffe efficiency is getting knocked down. Okay, an indicator of runtime, so how fast these models take to run. So with an upscale factor of 10, we're looking at around 4.5 hours. With 20, it's a little over an hour. 40, a little under an hour. And this result here shows that if you take the same upscale factor of 10 and just throw 4 times the number of tiles at it, you can knock it down by a factor of 4. So just showing you the sort of nice scaling of the model in parallel. Okay, now we're showing gauge accuracy when we compare the hindcast forcing, which is the stage 4 precipitation data, versus the forecast forcing, which is the quantitative precipitation forecast. And both of these forcings were the 6-hour data products. So now again, let's look at the highest ranked gauges. In this case, the hindcast is in red and the forecast is in green. So you can see that the hindcast has a little more variability captured in it compared to the forecast. In terms of the Nash-Sutcliffe efficiency, what we see is for the forecast, for the hindcast, it's around 90%, but when you go to the forecast data, it gets knocked down to around 50%. Over this gauge, again, 80% back to 60%. Mean absolute errors going from around a little under a meter to a little over a meter. And here we had mean absolute errors of just 0.4 meters, and then when we went to the forecast, it doubled it. So we do see some sensitivity in the best performing gauges. But if you look at the table here of the summary results, when you average over all the gauges, you start seeing that, well, gosh, there's not a huge difference on average for all the gauges, but we do see some difference some more significant difference in the best performing gauges. So mean absolute error doesn't change a whole lot with the forecast precip versus the stage 4 precip. And even if you go to like 1 hour stage 4, you're not going to get necessarily a big change in terms of mean absolute error. But we do see sort of a jump in the Nash-Sutcliffe efficiency, which is kind of an indicator of the ability of the model to capture some variability. And in that case, we're seeing the Nash-Sutcliffe efficiency being better with the stage 4 radar. Okay, so last thing I want to sort of, in terms of gauge analysis, we compared how well the model performs with a 3-day forecast versus sequential 1-day forecast. So the idea here is each day you get an updated forecast, and so use that information, put it in the model, and keep going. So when we do that, the 3-day quantitative precipitation QPF data gives you a mean absolute error of 1.26. With a daily restart, it's 1.22. So you're not seeing a big change here. Likewise, the Nash-Sutcliffe efficiency is a little better going with the daily restart, but not a lot. Moving on now, we're taking a look at high water marks as another indicator of model performance. So when we look at the high water marks, we can see across the region there's a bunch of dots here, and those are all locations where high water marks were recorded. And what we're color coding here is the error in the high water marks based on the water surface elevation reported in the Primo simulation. So we can see errors from -2 to +2 meters. So we compared the Primo model against the Fathom US forecast system, which was reported by Oliver Wing and colleagues. They also used a 30-meter resolution flow calculation. In Primo, we use 3-meter resolution topographic data upscale with a factor of 10 to give us 30 meters. In the case of the Fathom model, they're using a 30-meter digital elevation model. So you'd expect as you bring in more information about the topographic data, you're going to knock down the error. There's other differences in the models which make the direct comparison somewhat tricky, but we can at least get a sense of overall how these two models are performing. One thing to keep in mind is that we looked at a total of 518 gauges in this sort of broader Harris County type model domain, whereas the Wing et al. Looked at a larger number of gauges, over 1,000, stretched out over a larger area. So our model was focused on the urban areas, and the Wing et al. Study captured a much more larger swath of rural areas. It seems, looking at the data, that we're getting the biggest areas in the urban areas, and they are too. But what the colors seem to indicate is that the number of red circles here is smaller compared to what we saw in this model. That's kind of what you'd expect based on the fact that we're using better topographic data. The next performance indicator we're going to look at here are 311 calls. These are distress calls made during the storm. Each of these dots represents the location of a call. We've color-coded the dot based on what our model is telling us is the depth of that location. And you can see the scale of the used here on the left-hand side. So all we know is where people are and that when they called, they had flooding. So it kind of tells us presence or absence of flooding. So when we sort our model results based on presence or absence of flooding, we found that, there were basically over 1,000 calls here that we did not predict flooding. So we had a miss rate of like 32%. And then the remainder of the calls were areas with flooding. This gives us that's our estimate of the distribution of flooding across those calls. And we were able to predict 68% correctly with the model. The last performance indicator we're going to look at is freeway condition, and that's reported by the Texas Department of Transportation. So they're giving out road reports, things like a lane closure, shallow flooding, things like that. And so what we did is we summarized all the reports that occurred during the 5-day storm across Houston. There were 554 of them. We plotted out where they were, and we compared those reports against model predictions in Primo. And what we found is that these green areas are areas where the model predicted that the road would be closed based on a tolerance of 10 centimeters. And so those are areas of agreement. And we found that basically we had a hit rate of like 57% in terms of total road reports correctly predicted to be closed. And then the red areas are areas where the roads were reported to be closed, but we didn't predict a closure based on a tolerance of 10 centimeters. So we had a miss rate of 37%. Okay, let's wrap things up. So first, we looked at the sensitivity of this model to model fidelity. And so we increased the upscale factor from 10 to 20 to 40. We saw a reduction of the runtimes, and we saw a slight increase of the errors. And that was over 26 gauges. Some of the best performing gauges gave us errors of half a meter or so, which was doing quite well, and a Nash-Sutcliffe efficiency of around 90%. But then, of course, there's a distribution of gauges with different performance. So you get some sense of the sensitivity of the model to fidelity, and also the runtimes, which overall I think are more than adequate to make a five-day forecast that would be useful for decision making. So computational power is not what's going to be holding us up now. Secondly, we've got sensitivity to precipitation data. So when we looked at sort of the comparison of how well this model performs with the best available, hindcast precip data versus what you get in a forecast, you're seeing mean absolute errors go from around a meter to a little bit over a meter, so maybe a 20% increase. So you're doing not so bad going from hindcast to forecast. One thing to be aware of is you are catching less variability in the dynamics of the gauges with that forecast data product. So you might have a Nash-Sutcliffe efficiency of 50% in a hindcast, but it might get knocked down to say 30% on average in a forecast. In terms of sensitivity to daily forecast refresh, yeah, there's a really small sensitivity there. You can do better restarting every day, but it's not a radically different result over a 3-day time scale. And when we compared against high water marks, we saw a mean error across all the marks of around 8 centimeters, mean absolute error of a little under a meter. So we're doing okay there with respect to high water marks, and better than what was done with a model that used less accurate topographic data, which is what you'd expect, since most of the time topographic data is a primary driver of errors. A couple of other indicators of flooding we looked at: 311 calls and freeway closures, and we saw some skill there. So the take-home message from this talk is that forecasting a street-scale flood inundation is feasible with multi-day lead times, and we have enormous opportunities to inform emergency preparedness and response measures. Thank you very much. If you'd like to follow up, email contact information is down here. Thanks.